hierarchical models for meta-analysis now, which I think is the most promising way to deal with the kinds of aggregation problems we face in economics. So I'm going to walk you through the methodology. I'm going to talk about implementation. I'm going to show you our R package that we have, which is still on GitHub in beta. We're in the process of submitting it to CRAN. So if you start using it now, that means it might be more broken than you'd expect, but we'll answer your emails. If you start using it in a year, it'll work better, but we won't answer your emails. So that's the trade-off. Okay, so obviously the essence of science is replication. When we do evidence aggregation, which is not limited to meta-analysis, what we're trying to do is synthesize evidence to understand what, if any, replicable knowledge we've gained. And we don't want to assume replicability across contexts. That would be, frankly, insane. And so we need to measure it. We need to go forward measuring that. So meta-analysis is an important context in which aggregation occurs. We don't have much of a history of this in economics. People seem to prefer to write review articles. When I first started working on formal evidence aggregation when I was a grad student, initially the #1 pushback complaint that I got from faculty is like, why do we need this? We have review articles, right? So I can just look at the graph of the treatment effects and their standard errors, or I can just read the different papers, and I'll just draw my own conclusion. So obviously, that's crazy talk, and you wouldn't look at a scatter plot of X and Y and just like intuit your way to beta hat. So we've got to do formal aggregation. It's not that intuition is like, useless. It's very useful. It has a lot of nuance and can handle things to a level of complexity that, like, your brain is much more powerful than a laptop that you can buy. And in most universities, because of funding, it's more powerful than what they call their cluster. But, it's unreplicable. It's not transparent. And people do sometimes fall back on heuristics that we know are wrong. And so then you get into a big fight about such and such review article said this, the other one said that. So we're not going to have consensus if we do that, and then we can't move forward. So we'll be stuck debating what's the average treatment effect of microcredit for the next 50 years, which is going to be bad. All right, so microcredit is a case where we saw this start to happen. In 2015, 6 new RCTs that all essentially expanded access to microcredit services were published in the AJ Applied in a special issue. And Justin Sandefur, the Center for Global Development, made this graph where he's graphed here, the different countries in which the studies were performed. And then the dots are the treatment effects. The dark blue is profit, the light blue is consumption. And then the error bars are the 95% intervals, I think. So he's titled this graph, The Impact of Microcredit Varies Widely. And that was his takeaway from it. But what you can see is that almost all of the 95% confidence intervals actually contain not just an overlap with the other confidence intervals, but the actual point estimate of the other studies. So you're not going to be able to reject homogeneous effects in this literature in most kind of standard tests. And that actually is something that other people on Twitter pointed out, including Rachael Meager, who's now I think the chief economist at DFID, or whatever the title is at DFID. So people are having this fight over this. They didn't know what to do. The graph, I think, displays this problem pretty clearly and doesn't provide a solution. So then JPAL started to get involved. Sandefur also did something like this. So they created this table where they had these outcomes, then they had like the countries. So they included the Philippines, which is from a previous study. I think they did that because that's what I did. I'm not that sure. So I sort of talked to them about making this bulletin, and I said, like, please don't do this. This is a discredited methodology. Like, you shouldn't sit down and count up, 0 results and positive, significant, and negative. That's just not, there's a paper from 1998 that basically says, like, this is an atrocious process. But people are doing it anyway, and I think that's because, like, we don't have a practice of doing this kind of serious aggregation. And so until people come in and start doing it, this is what people are going to do. So working in this area, and I think Ava would agree, is one of those things that means you always have a reason to get up in the morning, because you're like, if I didn't get up in the morning, people are going to do this. So, okay. So, obviously, as Ava, I think, very eloquently pointed out, if studies, are in heterogeneous contexts, studying heterogeneous people, then the effects of the interventions that we study are almost certainly heterogeneous. So, in that case, you've got to be really cautious if you're trying to extrapolate or generalize the evidence to new contexts. But unfortunately, you're kind of stuck with that problem. You're always aggregating, right? Within studies, you're aggregating across individuals. You never see individual treatment effects. Some kind of aggregation is necessary, especially if you're making policy at international, national, or even state level. But also, like all science, as well as all decision-making, relies on extrapolation from past to future. So if you think that you can't extrapolate from Kenya to Tanzania, why would you think that Kenya last year is going to be a great guide to Kenya 10 years from now, right? When the policies that you're making are going to take effect if you're, building a subway or whatever. So, you cannot get out of this problem. We're going to have to deal with it. And people who are not dealing with this problem are essentially just closing off that part of the model and assuming that it doesn't exist and saying, no, I'm not really, I just do what's in my current sample. And then in the conclusion, they say, like, this tells us infrastructure does that, like, as if they did the work to extrapolate. Okay. So the error that you make if you do classical statistics that only has sampling error, and then in your conclusion you write, like, now we know that colonialism is good or whatever, is called extrapolation error. And I think it's fair to say that in economics we're committing just a massive amount of extrapolation error most of the time. But it's possible to estimate and quantify extrapolation error, and this is related to the random effects models that Ava talked about, and to adjust our total uncertainty for that error. And you're never going to see all the groups or subpopulations of interest, but as soon as you see more than one, or really statistically speaking, you need more than two, for reasons I'll explain, then you can estimate how well the groups approximate each other, and that tells you something about the extrapolation error you're likely to have for another group. Okay, so hierarchical models are models that contain both kinds of uncertainty, classical sampling error and extrapolation error across contexts or across populations. So the size of this extrapolation error, which is often what we think of as generalizability, transportability, or external validity, can be estimated by the heterogeneity in the set of treatment effects that we already have. Some part of that observed heterogeneity is sampling variation. So we don't want to count that. Confusing the two can lead to the wrong uncertainty estimate. So hierarchical models fundamentally take in data from multiple groups or places or time or sites, and they build a structure that allows but does not enforce parameter variation across those groups. So what that does is the model can then split out the within group variation, which you can often think of as sampling variation, or unmodeled within group heterogeneity, that's fine, and split that out from across group variation in parameters. This is an established old literature that people had been doing this sort of modeling for a while. So it's possible to do those in a frequentist way, but in practice, modern hierarchical and multi-level modeling is often a Bayesian exercise. So Bayesian methods always model parameters as random variables. So it gives you an immediate leg up once you're starting to say, like, oh, I think these parameters are like, they have some variance across settings. Like, well, only random variables have variance. So, it's sort of, if you're doing this in a frequentist way, you end up in this sort of like statistical twilight zone where you're saying, well, these parameters have variance, but the other parameters don't have variance. So this, if you just go full Bayesian, everything is like much cleaner. All parameters are probabilistic and you characterize your uncertainty about them. Bayesian inference is often very useful when you don't have a lot of different groups, places, or times, which is usually what we're dealing with in meta-analysis. You just usually don't have that many studies to deal with. And even if you do, that often means you don't have a lot of data within groups. So often there's just like kind of a slicing constraint, right? You can have a lot of one or the other of these. You usually don't have a lot of both. And if you take many of the popular frequentist methods and you apply them to small samples, they can be very misleading and overfit the data in practice. So that's something that we don't talk about a lot in sort of standard econometrics classes, but it is true. And so I'm going to talk about that a little bit more as well. And I think it's just very nice, especially in the context of extrapolation, to be able to put probabilities onto parameters, to say, like, the chance that we'll get an effect of this size in the next place is, this probability, or the chance that you'll get an effect above 0 is this probability. And you're going to get nice regularization from the priors, which leads to nice decision theoretic properties, and I will go into more detail on that as well. Okay, so Bayesian hierarchical models are also a super flexible framework. They can be applied to the summary statistics that Ava described, or they can be applied to full data sets, and it's not very hard to go between the two. The framework also allows you to compromise between a hardcore, what I'm going to call Cochrane type of view, where they extensively privilege the notion of fixed effects meta-analysis, and most of the handbook is about that. Although in section 16, they do say, like, gee, if you think there's heterogeneity, you should use this random effect stuff. And then there's this other view we have in economics, which I'm going to call the Pritchett-Mansky view, which is an extreme characterization of that view would be never aggregate, right? Like, it's just not going to work very well. It's not going to tell you something you need to know. What you should do instead is, like, think about the place you're trying to extrapolate to and just get a bunch of data about that place and then just, like, think about it in an economic way. So they're not a fan of getting data from other places to go forward into extrapolation. But these issues, which I think can seem kind of abstract, really underlie the debates about microcredit, deworming, vitamin A, BRAC, etc. And I've also put up a list of citations, although I think I'm citing like an old working paper version of your one. But yes, so by the end of this, you guys will be extremely familiar with Rubin's 1981 paper, which is called Estimation in Parallel Randomized Experiments, which is probably the first BHM for meta-analysis, although it's not the first BHM. Ava has a paper that's using BHMs to aggregate information. Ariana Bandiera and co-authors use them in the gender performance pay literature, and then I have microcredit. So those are kind of the four I think that are good to read. Okay, so let's get into the methodology. I'm going to do that, then I'm going to talk about the actual practical implementation, then we're going to look at microcredit. So I want you to think about a case. We have k different studies. More generally, you can think of this as just k different groups or places or times or whatever. You can call those sites. So I'm going to make this super easy. Let's think about randomized trials. So you have a randomly assigned treatment and control group in each site. So if you regress some outcome y on the binary treatment indicator t, this gives some average treatment effect under some hopefully reasonable assumptions. This afternoon, I'll talk about how those assumptions are less commonly satisfied than you'd imagine. But, and let's abstract away from, like, compliance and other issues. So we're just, like, regressing the outcome on the treatment indicator. Let's just say it's a treatment assignment indicator. So that's what you're dealing with. But when you have these multiple groups, you're typically not sure by how much the treatment effects differ across the groups. And how important that heterogeneity is. Obviously, that's the situation we face in meta-analysis, but this is also a situation that applied analysts face. And so an important case of that, and you can go and look at the Dean Carlin and co-authors 2015 science paper on the BRAC graduation program, which is called A Multifaceted Intervention Reduces Poverty in 6 Countries, or something like that. So they had 6 experiments that they loosely coordinated on doing, and then they didn't know about hierarchical models. So what they did is they ran 6 different analyses and they reported that, and then they ran one pooled analysis and they reported that, and they said, well, this is what we have. So they did not have a way to say which of these 2 answers is more useful, which one do we think we should be basing policy on. So that's the challenge that these guys were facing that they did not know how to solve. Okay. Okay, so here's what I just said. Again, as Ava said, it's really challenging because when they estimated this one pooled regression, they put fixed effects in, which means they put group-specific control means. That doesn't mean they did a fixed effects meta-analysis, although they, in this case, not because of the presence of the group-specific control means, but because of the presence of a common treatment effect that was shared across all the groups, what they did is close to a classical fixed effects analysis. So this is super confusing, unfortunately. We're stuck with these notational difficulties because of this interdisciplinary stuff. Okay, so this is an old problem that Dean and his co-authors had and that we all faced. Don Rubin got there in 1981 and others got there before him. And hierarchical models offer a statistical solution to this problem. Okay, then this is like trying to link this to the idea of extrapolation. You know, so instead of saying like, oh, which of these two analyses, the sort of 6 separate analyses versus the one analysis, which one of those is more useful, which one's more accurate, you know, I think more fundamentally, we really are thinking like, what should I think is going to happen in the 7th location that I do the BRAC graduation program? So that's an extrapolation question that really faces international development agencies and is the practical question of interest in much of social policy. Groups are really the fundamental causal unit, and I'm interested in knowing what's going to happen the next time I do something. That's the only space I have to act. But of course, you know, because we are dealing with such heterogeneous contexts, it might not be possible to get a good understanding of what will happen the next time you do something. So you might not be able to extract generalizable information about a given intervention. And so if we do seek that information, we should use a methodology that can return the answer that there is no such information. That in fact, you know, Lant's kind of suspicion is right and you can't really aggregate and you don't learn very much across settings or anything across settings. And so what we want is a methodology that's going to nest these sort of extreme positions or these extreme models that analyze 6 things separately and don't share any information across them versus analyzing everything together. And the hierarchical framework is going to do that for us. All right, so here is the definition of the problem for average treatment effect. So if you have k different studies in your literature, especially if you're a development economist, that means you have k linear regressions of an outcome on a binary treatment indicator. You might have some controls. It doesn't actually matter that much. In most of the cases I've worked in, like the outcomes are very poorly predicted by any covariate. So it doesn't actually matter if you control or not. And you probably will I will tell you a little bit why I think that is later this afternoon. Okay, so what you've got here, you've got n total households, and you've got your k different studies, you've run k different regressions. Each one of them has got this outcome, y sub nk for household n in site k, so that could be consumption, profit, whatever. And you're just, the simplest possible thing that you could do if you're a development economist is do a linear regression that has an intercept and a slope. So mu k is the control group's average outcome. Tau k is the difference between the control group and the treatment group's average outcome. So it's a treatment effect, the average treatment effect. So we do have an issue with notation here because tau is sometimes used as a scale parameter in meta-analysis textbooks. And I'm going to use it as treatment effect. And that's what some of the more economics random effects models do. So we are a little bit stuck with that. I apologize for that. Yeah, I guess I'm not sure how notation becomes standardized in methodologies, but I guess we're going to see over the next 10 years like what happens. All right, but then one thing is you have these k different treatment effect parameters, and the question that you're interested in is how do you go from this set of tau k's to the notion of a general parameter tau, which we're typically going to characterize the expected value of an element in this set. So what is the expected value of a draw from this set of things? And a closely related object is what should I expect the next time I literally draw from this thing, so the next time I do a study. So implicit in this, taking this expectation, which I'm taking across k, is a notion of a superpopulation. But I'm going to show you that we're employing that notion in a pretty weak way. We are not saying that the superpopulation, contains very much information or is very related. We're going to allow for the possibility that these things are almost completely unrelated. Okay, so it's equally crucial especially when we're thinking about extrapolation and the prediction of the next treatment effect, to estimate the variation in the set of treatment effects. And so I'm going to call that sigma squared tau. So again, apologize for the notational drama. We're just going to have to get through this. Okay, so since we've decided that we want a mean and a variance, I think the next natural thing that you would do is you would specify a likelihood function that has a location and a scale parameter. And the most nicely behaved and well understood such function is the Gaussian. And it has a lot of beautiful properties, which is why all these incredibly smart people used it. One of those properties is it's easy to use. So if I specified the above likelihood model, all of you would know how to estimate those parameters if you saw the tau k draws themselves. The problem is that you don't see the tau k draws. You see a noisy signal of those draws. And you know that those tau k hats, these point estimates, are subject to sampling variation. And so by the law of total variation, the variation in those observed estimates is strictly larger than the real variation in the underlying effects. The reason for that is that if I could rewind the clock and do exactly the same study in the same place at the same time, I would get a different answer because of sampling variation. That propagates up to the cross variation. We want to get rid of that part of the cross variation. We're not interested in that. So what we're going to do is specify a multi-level likelihood with variation at the local level, which we're going to think of as that sampling variation, and variation at the general level. So Ava already showed you one example of this in one way, but because these models are super strange from the perspective of like a curriculum in like PhD metrics, I'm going to show it to you again in a different way, and hopefully one of the two explanations will go into your brain. All right. So this is the Meta-Analytic Hierarchical Model from Rubin's 1981 paper. So I want you to first focus on the general level. That's just the likelihood that I just said we were interested in. So that's fine. That's saying that these treatment effects are actually drawn from some population. And we're saying that that's governed by a Gaussian distribution with a mean tau and a variance sigma squared tau. Yeah. Where is the microphone? Hopefully it's not in front of my... No, it's not.
My question's probably not...
Sure.
really important, but so you said that we make this Gaussian assumption because it's easy to work with, but is there any sense in which it might not actually be the correct distribution of the treatment effect?
Sure, absolutely.
Yeah. Okay, so can you say anything about thinking about that, thinking
Sure.
about how differently treatment effects might be distributed? And
Sure, absolutely. So I'm debating whether to put this off until I've explained the rest of the model. Yeah, let me explain the rest of the model and then do that. Yeah. Okay, so we've got this Gaussian distribution, which at this stage I largely justified to you based on convenience and nice frequentist properties. I'm going to get into that some more. But what's very important is that we also have this other level in the model. So if you focus on the lower line of this study level stuff, what you can see here is that we're using the information we have from the estimated treatment effects, so the tau k hats. And then we're using our knowledge of the original analyses that the authors performed in those studies. So we're saying typically these tau k hats are estimated via ordinary least squares regressions in contexts in which we can expect them to be unbiased, right? These are randomized trials and certainly consistent, even if they're doing fancy stuff. And we get a reported estimate of the standard errors. And we're usually, development economists and other economists are going to use the assumption of asymptotic normality to compute p-values. So, and indeed to compute confidence intervals. So the entire original studies are based on this kind of assumption. So the Rubin argument is that's for free, right? Like if that's wrong, the entire original study is wrong. Unless these guys are doing randomization inference or whatever, so Rubin's argument is that one's for free. We're not going to argue about that. I want to make the point that if you have the full data set, then the first thing you'd want to do is try to get as close to that structure as possible. So you want to get as close to replicating what the authors did as possible as a first step. Now, our authors did ordinary least squares regression. There is a likelihood way to replicate that. It's the Gaussian likelihood. Right? So if I just run my outcome and I say that the outcome is normally distributed, no matter how disgusting and non-normal it looks, if I say it's normally distributed, it's got this conditional mean structure, which is the linear regression, and it's got some standard error, it's got some variance. I shouldn't say standard error, it's got some variance, then that maximum likelihood is analytically identically the same point estimates as ordinary least squares. And under the homoskedasticity assumption, it's the same standard errors. And Ulrich Müller is doing all this work on, like, here's how you do heteroskedasticity in this framework if you really want to. So the reason for that is that the kernel of the Gaussian is a least squares object. That's also part of why Gaussians are so nice and perform so well even when they are incorrect. And we will get back to that. So I think the most common objection at this point, and Ava talked about this as well, we just had this question, which is like, all right, maybe we can go with you on this sampling error being Gaussian, right? If we're going to challenge that, we got big problems in this literature. My second paper is like, you guys were basically saying like, everybody's freaking out about this. Actually, this assumption is way more suspect than that. Okay, so, but for now, you don't know that yet. So let's say you're much more worried about this assumption. So let me give you a couple of reasons why this is still the first thing you should do when you open your data set. So this structure actually nests all the commonly done meta-analyses. In particular, it nests the fixed effects model. So I'm going to show you how in a minute. But basically, if you were to set sigma squared tau to be 0, the weights that this model would place on the tau k hats to estimate tau are the fixed effects weights. So this model is estimating sigma squared tau. It is perfectly capable of estimating sigma squared tau to be essentially 0 and then implementing the fixed effects model. So, of course, it will be up to a degrees of freedom correction. It will lose a degree of freedom by having estimated this thing. It will also be challenging because sigma squared being 0 is on the boundary of the parameter space. Was that why your hand is going up? Or no. Okay.
The other extreme.
Yeah, exactly. Right, okay. So the other claim that I'm making is that this is nesting the no pooling model. And the no pooling model occurs when sigma squared tau is practically infinite. So what that means is it needs to be very, very large relative to the scale of the rest of the problem. And if it is very large, what happens is you put your tau k hats into the model. It will estimate an extremely large sigma squared tau, many orders of magnitude larger than anything else that you've put in. So you put your tau k hats in your standard errors. It will estimate tau, but the uncertainty will be massive. And then, so this model always re-estimates the tau k's. And I'm going to explain why in a minute. But what will happen if sigma squared tau is huge is that the re-estimated tau k's will just be the original tau k hats that you put in the model. So in practical purposes, like your computer will rarely actually spit out INF as an answer. It can do if you're very unlucky like me. So your computer can and sometimes does return the answer INF. Now, usually your advisors will say, you made a coding error if that happens. I regret to inform you that that's not necessarily the case. There are numbers too large for the computer to store. That's awkward, but it's true. And so what we're really talking about in practice is the model can estimate a value of sigma squared tau that is so large that it refuses to implement any kind of information sharing across the settings. So you put in the 6 or 7 different estimates or whatever into the hierarchical model, and it spits out the same 6 estimates and says you did not learn anything from trying to combine this information. So that's a pretty strong signal that there's a lot of heterogeneity across the studies. But I think what's really interesting and important, and this is the point that Ava made in her job marker paper, is that this model can implement partial pooling, right? So there's just no reason why you would think we live in a universe where either the effect in Tanzania is exactly the same as Kenya, or you learn nothing about Tanzania from Kenya, right? The truth is probably that you can learn a little bit about Tanzania, or maybe even a moderate amount about Tanzania from Kenya, but certainly not perfect, but not nothing. You have a comment on that?
Oh, no question.
Oh.
So in practice I guess it would be great to hear more about circumstances in which you do get these very large sigma squared tau. Because my intuition is with a small number of studies, that it's small number of studies that the normal is going to be upper level is going to be doing a lot of work, and so yeah.
So unfortunately, it depends a little bit on the factorization of the data. So like even if sigma squared tau is very large, you can get a realization of the data that if you haven't chosen your prior that carefully, can lead you to the wrong place. I haven't seen that happen very often in the simulations that I've done. So it's not something that I'm like generically concerned. Like I have seen cases where the model just spits out the inputs again. Yeah.
What's the nature of the, like? So
they're just super far apart on the real line and they're precisely estimated. Yeah. So that's basically, what you're dealing with. Like, I've also seen it like be close to that, but not fully. Yeah. So I think I have, let me speak a little bit more generally to this question of like, okay, so the argument that I just made to you is like, what's nice about this Gaussian structure is it nests these two extremes that people are trying to implement anyway. Okay, so that's cool. However, you might think like, I can do something different than that. If I have good information that in fact one of these structures is not Gaussian, I should use it. So that's true, but that information better be good. Because once you move away from the Gaussian, you move away from these kind of nesting results, and you're moving away from the nice like shrinkage and asymptotic results. Shrinkage is just how much the tau k's are like pulled together. So I think the most important thing to be worried about is skewness of treatment effects at the upper level. If you think that the treatment effects for a scientific reason are skewed, so for example, risk ratios can't be negative, distributions that are bounded below and not bounded above tend to be skewed, then you want to use a log normal or just take the log and use the normal. In general, unless you have a skewness problem, you're probably going to get pretty good characterization of the mean and the variance from this model, even if the normal assumption is wrong. So McCullough and Newhouse 2011 is a citation for that. I also have like a working paper that unfortunately I cannot post because it pertains to medical stuff, which they don't like to circulate papers, but that also shows that this model is very robust to weird violations of the data generating process in ways that fixed effects actually isn't. Okay, so let's move on. That is the soul of that thing, and just to illustrate, if sigma squared tau k is known, then the estimation of tau is done by combining the tau k hats using a proportional inverse variance weight, but this is the total variation. So that includes the sigma squared tau. Now, full pooling or fixed effects, as Ava described, is an inverse variance weight, but using only the sampling variation. So literally, this weight is a subtype of the upper weight. Okay. I also want to talk about shrinkage. So what's really nice from the perspective of learning about what's going on in different places is that this model will actually give you a better estimate of the tau k's themselves, as long as you have 3 or more. And that's actually true even if, in fact, the tau k's are not related. So I think I have this later in the presentation, but just keep that in your mind. Like the tau k's don't have to really be related for this to be true. It's called the James Stein result. Blew up statistics for about 40 years. Okay, so the challenge is if I knew sigma squared tau, I could just implement that weight, but I don't know sigma squared tau. So I'm going to need to jointly estimate all this stuff. Formally speaking, this is a deconvolution. Okay, so actually, a bunch of regressions is not going to do this in a good way. So we're going to have to do some pretty gnarly stuff. In the interest of time, I think Ava already described the ways you could do this using frequentist stuff. What's so nice about Bayesian inference is that we're going to be jointly estimating all of these unknown parameters in one object, the joint posterior. And that's going to allow us to characterize potential dependencies in the uncertainty we have about these objects, which is inherently arising in the hierarchical model case, because what you believe about sigma squared tau strongly affects what you believe about the tau k's and vice versa. So when you do that, that gives you a framework to have coherent prediction intervals on tau k plus 1. So the challenge here is when you come to generate uncertainty on the next draw, you need to propagate the fact that the uncertainty that you have from the fact that you don't even really know the mean and the variance of this Gaussian from which you're drawing this object. So it's not just that you have uncertainty because you're drawing something from a random variable. You don't even know the parameters of that random variable. So you need to propagate that uncertainty. The challenge is that frequentist methods like empirical Bayes maximum likelihood typically do not propagate that uncertainty, and certainly don't do it automatically. The Bayesian analysis is going to do that automatically. It's not that easy to implement. You need to use Markov chain Monte Carlo methods. It's not that easy to implement until we made the R package. I'm going to explain what those are, but in order to be sure that those things are converging to something reasonable, in most cases you'll need to specify priors. So if you're willing to specify priors, and we'll talk about that as well, then the models are going to be admissible, consistent, asymptotically Gaussian, and have all sorts of nice properties. They're also going to do regularization. So because I've talked about this a little bit, and I know not everyone's familiar with it, let me give you one slide on that. So regularization is the act of introducing new information into a prediction or estimation problem in order to prevent overfitting of the sample. So overfitting is when you fit the sample at the expense of fitting the population or learning about the population. You can think about that as fitting the noise, not the signal. So you're literally, in practice, just adding a constraint to the model fitting algorithm. So the prior constrains, you can think of the prior as constraining the maximum likelihood. That's one way you could think about it. And so technically you're adding something to the model, but in practice you're reducing the complexity of the fitting problem, right? You're cutting out bits of the parameter, or you're penalizing bits of the parameter space. So the algorithm needs to explore less parts of the parameter space. So Bayesian priors will do this. It's often comparable to machine learning regularization. So ridge regression is just a Gaussian prior on regression coefficients, set it at 0. Meta-analysis is often a very small data problem which benefits from regularization. So in the microcredit case, I had 7 studies, and I'm trying to estimate a mean and a variance at the upper level of 7 things. So the core challenge for estimation at that scale is variance and not bias. So basically, I think if you're worried about like statistical bias in meta-analysis, this is the wrong concern to have. You can be worried about like publication bias or sample selection bias. Those are different. But if you're worried about econometric statistical bias, this is totally the incorrect thing to be worried about. The problem for estimation at the scale that we're at is variance. So you should be happy to introduce some bias to get rid of the variance. So we're going to tell John Ioannidis that. Okay, so this is my empirical Bayes. I think Ava covered Bayesian metrics of generalizability very well. I want to point out that this framework that I just showed you is very flexible. So, suppose that you want to incorporate information on the control group's means, the mu-k's that we had in the previous slide. Well, that's fine. You can build a joint hierarchy on mu-k and tau-k and say, okay, these things are actually jointly normal. So that's also what's nice about normals, because they're essentially the only smooth multivariate distribution. As Andy Gelman says, there's also the multivariate student T, as if that's a different distribution. And then you've got this variance-covariance matrix. Again, you're going to have a big problem estimating, in particular, the off-diagonals of this matrix. Now you're estimating a correlation of 7 pairs. Okay, you need to regularize that. So that's what I've done in all my papers, is regularize that parameter. Now, the extreme frequentist thing you would do is say, oh, I can't estimate it off 7 pairs. I'll set it to 0. So that's just dogmatic regularization, right? So here we're going to do smooth regularization and say, I think it should be pushed towards 0, but I won't enforce 0. All right, now what if you think I have covariates that explain the variation across the sites in the control group averages and the treatment averages? So this is the Bayesian hierarchical version of meta-regression, right? So meta-regression is I've got tau k's and then I do some OLS beta 1 xk, right? So here we have a much more subtle and nuanced framework that allows us to say, all right, we've got this stuff going on here, this stuff going on there, there's correlations here, and we can use priors to discipline the fit of this problem. So it's just much more flexible. Okay. All right, so here's what I had. This is my answer before you can get the McCullough and Newhouse citation if you want. Okay, so let's talk about implementation, because I think I only have 10 minutes, right? Yeah, okay. So how are we going to do full Bayes? It's not that easy. This is more propaganda. Okay. So you guys know that if you have some multivariate data W and some parameters theta, you know how to specify a likelihood, right? W, in some sense, conditional on theta, or taking in theta as parameters that govern its distribution. But now we want to think about an object that captures our uncertainty about the unknowns given the data. So that's the posterior distribution, the distribution of theta given W. So we can get that from the likelihood using Bayes' theorem, but we need a prior. And if you are willing to specify a prior on theta, then you get the posterior distribution using one equation. And this is the probability distribution that characterizes our uncertainty about theta given the data that we see. That's all it is. This is, and as Neil Shepard says, the reason why you would do this is because this is true. There's no other way to get this distribution. That's it. Okay. So posterior distributions combine information in the data via the likelihood and information from outside the data via the prior. So the most common critique of Bayesian methods that you'll hear is that this is unscientific because things shouldn't come in from outside the data. But all of statistics is about bringing things in from outside the data to understand the data better, right? So like, what is an exclusion restriction? That doesn't come from the data. That comes from knowledge that you have outside the data set. There's no place in the data set that you can find the exclusion restriction, or you can't even test it most of the time. All right, so where does the prior come from? So according to Olivier Blanchard, the same place that the likelihood comes from, right? It comes from your knowledge of the problem. How do you construct a likelihood? Same general principles to construct a prior. There's also literatures on like the nice functional forms that perform well in certain circumstances for priors. So there's a bit of a cheat sheet. So I would tend to use a diffuse normal on location parameters like means. And I would tend to use either a half Cauchy or a half student T or a very, very diffuse uniform on scale parameters. For hypercovariance matrix, there's a whole literature on that. Of course, it's not good if very small changes in the prior cause large changes in the posterior, unless you're using the prior to regularize, in which case that's unavoidable. So you want to check that, and we have some ongoing work about that. Okay, so just to give you a sort of indication of how bad this problem is, so the model that I showed you before that has this joint hierarchy on mu k and tau k, this is the posterior distribution. And this is not a known distribution. So this cannot be characterized in the computer analytically. Okay, so we don't know what that distribution looks like. Now, if I plug in data to it and parameters, I can evaluate it, but I can't generally characterize it. So what Markov chain Monte Carlo methods do is they allow you to draw samples from a distribution that you cannot analytically characterize. The way they do that is by constructing a Markov chain which has the posterior distribution as its invariant limiting distribution. And so in the limit, the draws from the chain are ergodic draws from the posterior. So as good as IID in most cases. So this is done using probabilistic accept-reject rules on proposal distributions. It's not rocket science. Well, it is rocket science, but you can do it on your computer now. So I want to give a little bit of a caution. So you used to get taught to do Metropolis-Hastings algorithms or Gibbs samplers. So those are going to struggle on hierarchical models because of the strong correlations between the parameters. So they're going to start wandering around the space, and it's going to take a very long time to converge. They're super inefficient. So what you want to use is Hamiltonian Monte Carlos that do a lot better on these problems, not on all problems. Primarily because they use the Hessian information. A very good package to use is Stan. It has a bit of a learning curve. We want, I think in general in this room, for people to do more meta-analysis. So what we have at the moment is a package that allows you to do, like to fit the models I just showed you in one line of code. And then here's my, don't use Stata's MCMC pack or Bayes pack for BHMs. It's fine for normal Bayesian regression stuff. But it uses Gibbs samplers and Metropolis. So and it will not tell you that the thing is not converged. So for other Bayesian stuff, fine, but for hierarchical models, no. Okay, so let me tell you a little bit about Bagger. So Bagger is short for Bayesian aggregator, and it is co-authored with Witold Więcek, who's a much better programmer than me. So it's designed to run by default. If you need to install Stan, that is the hardest thing about using Bagger. So you have to go to the rstan instructions and install it. That's a pain in the ass. That takes 20 minutes, depending on how much you've gussied up your machine. So basically, you need a C++ compiler that R can talk to. And depending on what you've done on your laptop, that could be easy and take 5 minutes, or that could be hard and take an hour. Once you have that, you can run, so for example, out of the box, if you download and install and load Bagger, and then you put your estimated treatment effects and your standard errors into a data frame, and then you run the command Bagger on that data frame, it will automatically fit the Rubin model for you, it will choose priors for you, and it will test the convergence. We also have automatic plotting and leave one out cross-validation already, and we have the other models as well. So if you go to the GitHub for Bagger, you can download it and get started. So let me show you just quickly the installation. So that's what it takes to install it once you've already installed Stan. Your computer then has to compile the Stan model, so this takes 5-10 minutes as well, but you don't do anything. And then you literally would just run Bagger. Let me show you actually on this machine. I have it. Let's go to the console. Okay, so I literally just reinstalled it, so let's load it. Okay, yeah. Oh, sure. View. Tools, global options. Oh, yes. Oh, this is very... Okay, font size, what, 14? Yeah, that looks good. Okay, all right. Okay, so we have Bagger. And then, so let me show you schools. Okay, so this is Rubin's 8 schools data set. So you've got tau is his treatment effects, as Ava's notation showed you. You've got the standard errors. So now you want to totally replicate Rubin's analysis. So you type Bagger schools. It runs a model for you. It tells you stuff about, so in this case, 8 divergent transitions is not too bad. It tells you what type of model you ran, the Rubin. It tells you you did partial pooling. That's a classical Rubin. This model can also do no pooling or full pooling if you specify. It tells you your aggregate treatment effect, so the mean of your upper level distribution and the 95% interval on that mean. It tells you the standard deviation of that upper level distribution and the 95% interval of that standard deviation. And then it tells you the updated treatment effects in each of the sites. So this used to take ages to do on your own. I see the pain in Ava's eyes. But now you can do it like that. So that is much, much easier. And this package can also take in full data sets, and it will try to figure out which bits. You can also specify which bits you're interested in. Okay, so let me go back to this. Although, do I have, 5 minutes or no? Done.
Run a bit over into the break if you want.
Okay, so let me take 5 more minutes to talk about microcredit then, and then we'll be done. How do I view all of it now? Now I cannot. Window. There we go. That's right. I got confused with the RStudio. Okay, so this is some slides about how come it's so much better. If you're interested, you can read them later. Okay, so we did this on microcredit. So if you do that on the different outcomes, if you do the Bayesian hierarchical model versus if you do full pooling, then you do get a somewhat different answer. And it's interesting, you can see it's not always that you're less, it's not always the case that you're going to be less confident if you're doing this extrapolation era exercise. So depending on how much sampling error there is, you could be more confident accounting for this. But you can see here, there's not that much difference in how uncertain you are if you use the 2 methods, if you look at that average effect. But if you now look at the prediction, then the Bayesian model is telling you should be substantially more uncertain if you're trying to make a prediction about the next place than what the full pooling model would imply. So this is, for example, the original profit point estimates that were estimated in the studies. And then the red is what you get once you do the partial pooling. So this is actually a substantial amount of pooling, about 60%. So you're learning a lot combining this data set. Now, it is still very, very far from homogeneous. right? So this is not a case where you'd say like, oh great, we'll just use fixed effects. That is not the takeaway from this. Like, you need to use these kinds of models, but it's not that all hope is lost and you can't learn across settings. You can. You can start doing these models splitting out by covariates if you want. In this case, we can see that the people who had previous business experience have much more uncertainty, but also seem to have more going on. And that's going to spill over to the prediction as well. I want to also say, people want to know which covariates at the study level predict or explain the variation in treatment effects. That's meta-regression. You can't really do that, as we talked about. So this is what I think is the best that you would do, is you would do a pretty punitive ridge regression on this stuff, and then you would report the absolute magnitude of the coefficients. As long as that relative ordering is stable, I think that's good information. In this case, it was pretty stable. It's not completely stable. But what you see here is that things like targeting women and the interest rate are much more predictive than like what the baseline or like control level of profit or consumption is, and what is the randomization. And this is like, when I started doing this, people said you should not aggregate these studies. They randomize different units, right? That is actually way less important than the fact that they offer different interest rates, right? So it's, I think, and that, let me close by linking that back to exchangeability. I think ex ante, what people were saying to me is, you're a fool for making an exchangeability assumption when there's these clear two groups of different randomizations. You should analyze these group by group. Okay, so my take was like, I don't know that that's the important covariate. I can think of 10 other important covariates, right? Because I don't know which of these covariates is the one to use, and I can't use all of them because I don't have enough data. I'm going to use none of them to start off with. And that was the right call in this case, because the one that everybody said is the crucial one is not important. So let me close with that, and hopefully we'll have more time in the second half, and sorry for going over. Okay. Oh, yeah, sure.
So would you say then that it is difficult to specify a priori how you're going to, so you couldn't say, before you did the, like a systematic review, you wouldn't be able to say, I'm going to pool together the studies that had different interest rates or not. So you can't pre-specify any of that. It's got to be driven by the data.
So I think we're not in a place, like hopefully in 100 years, we'll be in a place where we know enough that we could do it. And I'm optimistic that we'll get there. We are not there now. I think it's totally disastrous for people to go. The other thing people would say is they'd be like, why don't you standardize these by their control means or whatever? And it's like, actually, you should standardize them by the interest rate. But you don't know that until you've done the proper analysis. And also, that conclusion, I'm really only comfortable with an ordinal conclusion, right? The interest rate seems more important. I can't tell you what the right standardization is by that thing, because I'm not confident. Like, I can't detect the right functional form on this thing. I have 7 pairs. So I think exchangeability is crucial because we just don't have enough information about what's important. And I would say it's astounding, and I think Ava shares this view, that it's astounding to me that people will say, I cannot put even a week prior on what I think the average treatment effect is, but I know which covariate I should regress on. Like, and I'm 100% confident in that, and I don't need to do any kind of, it's just crazy. So that would be my take, and I hope it would be co-signed by Ava, yeah.
Yeah, because I think that's super important. It's like you have to specify what's going in the systematic review, but you may be deciding that you don't have enough information to include some of the studies, or that's a big shift, I think, from how a lot of reviewers and people think about how you use the full data set. I
agree, yeah. And I think, like, in some ways, like, people focused a lot on, like, oh, you have these Gaussian assumptions, and actually, like, probably the 2 weakest parts of the analysis I just showed you are the assumption that the sampling error is Gaussian, because that assumption turns out to be extremely bad in this setting, and the fact that I only used randomized trials. Okay, so I'm not advocating for just naively combining observational and experimental, because they're different, but it's not optimal to just leave them out. It's easier, and like makes the people who control journals happier, I did it because it's easier, just for the record, not strategically. But I think we want to go to a place where we're building this bigger and bigger tent, and then saying, all right, let's say these things might be different, and yeah, we're going to have to put a prior on that in order to make traction on it. But the alternative to that is just like arbitrarily excluding stuff. So that's not good either. Yeah, let me cede the floor.